Welcome to today's episode, where we're diving into the world of embedded systems. Let's kick things off by defining what an embedded system actually is. You've seen these all around you. Think about your washing machine, microwave, or even the remote you use to turn on your air conditioner. Each of these is an embedded system, a combination of hardware, software, and sometimes mechanical parts designed to perform a specific task. That's key here, one specific task. Now, what makes an embedded system different from, say, your personal computer? Computers are meant to handle a variety of tasks, whereas embedded systems have one job to do. Take a washing machine, for example. It's built to wash clothes, and every component in that machine supports just that goal. There's hardware like buttons and circuits, software on the chip that controls wash cycles, and mechanical parts to agitate the water and spin the drum. Pretty fascinating, right? Brief history. Let's roll back in time a bit. One of the earliest and most significant embedded systems was the Apollo guidance computer, designed in the 1960s for the Apollo missions. It was a breakthrough, with only 4 kilobytes of ROM and a processor running at just over 1 MHz. Fast forward to the 1970s, and Intel introduced the 4004, the first commercial microprocessor, which set off a wave of innovation in embedded computing. Types of embedded systems. Embedded systems come in various types, so let's break them down quickly. Standalone systems. These work independently, like a microwave or a digital camera. Real-time systems. They operate within strict timing constraints. For example, car airbag systems. There's no room for delay. Networked systems. These are connected to a network. Think about home security systems, where cameras and sensors connect to your smartphone. Mobile embedded systems, portable devices like your smartphone, which is pretty complex with multiple tasks embedded within it. The design process. Moving on to how embedded systems are designed, it's a step-by-step process. Designers start by capturing system requirements, understanding what the system needs to accomplish. From there, they specify and design the architecture. After that, they build hardware and software components, followed by system integration, where everything is put together and tested. A critical part of the design is balancing factors like performance, cost, power consumption, and physical size. Hardware components. Now, you can't talk about embedded systems without mentioning some classic hardware. The Intel 8051 microcontroller, for example, is a superstar in the embedded world. It's an 8-bit microcontroller that's easy to program and highly versatile. For more advanced applications, ARM processors, with their power-efficient RISC architecture, are also widely used. Input and output. For an embedded system to be effective, it needs to communicate. There are 5 major methods for handling input and output. Main thread polling, simple, but it requires the system to keep checking for input. Multi-thread polling, a bit more advanced. Here, a separate thread checks for input. Interrupts. When the system gets an interrupt, it pauses other tasks to handle input. Interrupts with threads. This combines interrupts with threading, making the system more responsive. Direct memory access, DMA. This takes things up a notch, letting data transfer directly to memory without interrupting the processor. Memory types. Embedded systems use different types of memory for various functions. RAM is essential but volatile, it loses data when powered off. For storing long-term data, non-volatile memory like ROM, flash, or EEPROM is used. Embedded systems also use cache and memory management units, MMUs, to handle memory efficiently, especially in complex systems where virtual memory may be needed. Interrupts and controllers. Interrupts are a core concept in embedded systems. They allow the system to respond to events instantly, like pressing a button on a remote. Handling multiple interrupts efficiently often requires an interrupt controller, which prioritizes them based on urgency. Closing thoughts. So, embedded systems might be small, but they are incredibly complex and powerful in their own right. They're at the heart of so many devices we use daily, each with a design and function that supports a single, dedicated purpose. It's amazing how they keep getting more advanced, with faster processors and more efficient memory. That's it for today's deep dive into embedded systems. Safe travels and happy listening.